Hello. In the previous lectures, we have learned about the Fuchsian group and its action on the hyperbolic plane. So in this lecture, we'll be learning about the properties of commuting elements in PSL2R. Okay, so let us begin. So first, we'll be proving this lemma. So this lemma, it says the following. So suppose you take two elements of this PSL2R and they commute with each other. So T and S, so this belongs to your PSL2R, and S compose T is equal to your T compose S. So then we'll prove that, so this S, it maps fixed points of T to fixed points of T. So this fixed point of T, so this is invariant under the map S. So the proof is very easy. So let us take alpha to be a fixed point of T. So T of alpha is equal to alpha. Now you apply S on this thing. So ST alpha is equal to S alpha. And we know that ST equal to TS. So therefore, so we have T of S alpha is equal to your S alpha. So this implies that T of S alpha is equal to S alpha. So this implies that, so this S alpha, so this is also fixed by T. So S alpha, it belongs to the fixed point set of this T. And this implies that, so this S of fixed points of T is a subset of fixed points of T. So these two are finite sets. So fixed point set of T is finite set. In fact, the cardinality of fixed point set of T is less than equals to 2, because this T is a Mobius transformation. And also this S, it is a bijection. So therefore, cardinality of this S of fixed points of T is equal to the cardinality of the fixed point set of T. So because of that thing, so you have this equality. So we have this equality. Okay, so now we have proved this lemma, and now, so we are going to prove this theorem. So what is this theorem? So let us take two non-identity elements of PSL2R, and suppose they commute with each other. So then we'll prove that, so they have same fixed point set. And the converse is also true. So if I take the fixed point set of two elements of PSL2R to be same, so then they will commute with each other. Okay. So now let us prove this thing. So suppose we take S and T, two elements of this PSL2R, and they commute with each other. So ST is equal to your TS. And we also assume that they are not identity elements. So the claim is the following. So fixed point set of S is same as the fixed point set of T. So now this fixed point set of T, it can be at most 2. Go case by case. So let us first assume the fixed point set of T contains only a single point, namely this singleton set alpha. So here T of alpha will be equal to your alpha. And so this S commutes with this T. So this will also imply that from this lemma, so fixed point of T is singleton set alpha. So from lemma, it will imply that S of alpha is equal to your alpha. So this comes from the lemma. So S of alpha is equal to alpha, and alpha is also a fixed point of S. So what we are going to show is that the cardinality of fixed point of S is just 1. So fixed point of S, again, it is a singleton set. and it will be, so we have already proved that alpha belongs to your fixed point S. So we'll prove that fixed point set of S is just the singleton set alpha. So suppose we take another beta belongs to your fixed point set S. So beta is not equal to your alpha. And again, by the previous lemma, so we can prove that T of fixed point set of S is equal to the fixed point set of S. So this means that T of beta, it belongs to your fixed point set of S. And so we have taken beta belongs to the fixed point set of S and beta not equal to alpha. And because this S is, it is a Mobius transformation, so the cardinality of this fixed point set of S is less than equals to 2. And alpha beta, it belongs to fixed point set of S. So therefore, fixed point set of S, it will be exactly equal to this set alpha beta. And now T is again it is an isometry. So T of fixed point set of S is equal to the fixed point set of S. So T of alpha beta will be equal to alpha beta. So T of beta, so fixed point set of T is just a singleton set. So therefore, T of alpha is equal to your alpha. And T of beta, it cannot be beta because fixed point set of T is exactly the singleton set. So T of beta is equal to your alpha. So this proves that this T is not a 1-1 map. So this is a contradiction. So this is a contradiction. So this contradiction, it proves that fixed point set of S is just the singleton set alpha, and which is nothing but equal to your fixed point of T. Okay, so now let us assume that the cardinality of fixed point of T is equal to 2. So that means that, so T fixes 2 points. So if T fixes 2 points, so this T has to be a hyperbolic isometry. So T has to be a hyperbolic isometry. And I can get some isometry F such that FTF inverse. So this will fix 0 and infinity. So this has been done in some class. So therefore, so without loss of generality, I can assume this T, it fixes 0 and infinity, and T is of this form lambda z. So again, I will repeat that thing. So suppose T, it is a hyperbolic isometry. So we'll have an axis of this hyperbolic isometry T. So I can have some isometry F such that FTF inverse. So this will again be a hyperbolic isometry, and this will fix the imaginary axis. So that is the imaginary axis of that conjugate FTF inverse. So that will be imaginary axis will be the axis of that FTF inverse, that conjugate. And FTF inverse, so that will be of the form z goes to lambda z. And so what we'll do, so we'll work with that conjugate. So therefore, without loss of generality, we can assume that, so this Tz is equal to your lambda z, and also we can take this lambda to be greater than 1. So therefore, this fixed point of T is equal to 0 infinity. And now, so this S, it takes fixed point of T to fixed point of T. So again, so let me recall. So you are assuming this thing that St equals to Ts. So this means from this lemma that S of fixed points of T is equal to fixed points of T. So therefore, S of 0 infinity, so this set will be again this set 0 infinity. And now, so this possibility can happen. So S of 0, it goes to infinity, and S of infinity is equal to your 0. So if I assume S of 0 to be infinity and S of infinity to be equal to 0, And this sz, suppose this is of this form, az plus b by cz plus d, where this ad minus bc is equal to 1. Because s0 is infinity, you put z equals to 0 in this above equation, So what you will get, this d is equal to 0. And if I put infinity, so s of infinity equals to 0, so then what you will get, a equals to 0. So sz will be of this form, b by cz, and a is 0, d is 0. So therefore minus bc is equal to 1. So therefore this sz is nothing but minus b square by z. So therefore here, so what we are getting, so if I just take s of ib, so this will be equal to your ib. So the fixed point of s is just the singleton set. So here so what we are getting here, the fixed point of s is only the singleton set. And again, so we have this observation from the previous lemma, t of fixed point of s is equal to fixed point of s. So this implies that t of ib is equal to your ib. So this proves that the fixed point of t, we have assumed it to be 0, infinity, and now again we are getting another distinct complex number ib. So cardinality of fixed point of t is greater than 2. So this cannot be possible. So this is a contradiction. So why this contradiction? So this contradiction is because of this assumption. So because of this assumption, so we have a contradiction. So s of 0 equal to infinity and s of infinity equals to 0. So this cannot be possible. So this cannot be possible. So s of 0 has to be 0 and s of infinity has to be infinity. So this is a contradiction. So therefore, so what we have showed from here, so fixed point of s is again 0, infinity. So we have shown that s of 0 is equal to 0 and s of infinity is again equal to your infinity. So therefore, so what we have, fixed point of s is equal to 0, infinity, which is again equal to the fixed point of t. Yeah. So we have shown this thing. So we have taken two non-identity elements s and t, and they have they commute with each other. So first we have taken this s singleton fixed point of s to be a fixed point of t to be the singleton set. So in that case, t can be parabolic or elliptic, and if fixed point of t is uh, 2-point set, so then this t is hyperbolic. So we have proved that. So if the two elements commute with each other, they have the same fixed point. Okay, so now let us come to the converse part. So let us assume that fixed point of s is equal to fixed point of t, and we have taken this s to be non-identity and t to be also non-identity element. So first let us assume that this t to be hyperbolic element. So again, without loss of generality, we can assume this tz is equal to your lambda z, where you can take this lambda to be greater than 1. So fixed point of t is 0, infinity, and we have assumed this thing. So fixed point of s is equal to fixed point of t. So fixed point of s is 0, infinity. So therefore, and s is non-identity element, so then s has to be of this form. So sz is equal to mu z for some mu not equal to 1, and mu is positive. So tz is equal to lambda z, Sz is equal to mu z. So T compose S of z. So this will be equal to your lambda mu z, and S compose T will be equal to your mu lambda z. So those these two isometries are same. So therefore T compose S will be equal to your S compose T. And now let us assume this T to be parabolic. So again, without loss of generality, we can assume this Tz to be of this form, equal to Tz is equal to z plus a for some a which is not 0. So a is a real number which is not 0. So fixed point of t is the singleton set infinity. Fixed point of t is equal to fixed point of s that we have assumed. So therefore, fixed point of s will be equal to the singleton set infinity. And again, so this s, it is non-identity isometry. So Sz will be of this form, Sz equals to z plus b. So therefore, what we have, so Ts will be equal to your Sz. So if I compute this composition, so T compose S, so this will be your Z goes to Z plus B plus A and S compose T, so this will be your Z goes to Z plus A plus B, and A plus B is equal to your B plus A, so that's why we have this thing. So T compose S will be equal to your S compose T. And if I assume this T to be elective, you can proceed similarly. So in that case, with the loss of generality, you can assume this T map to be Tz, the matrix of this T to be your cos theta, sin theta, minus sin theta, cos theta. And you can proceed similarly. Okay. So now we have this following important theorem. So let us take F to be an element of this PSL to R. And we'll denote this G to be equal to your PSL to R. Then the centralizer of this F in this G. So what is the centralizer? It is a set of all group elements G such that GF is equal to your FG. So G and F, they commute with each other. Okay. So now if I assume this F to be hyperbolic isometry, so it means that fixed point of F, it is 2-point set. And if I take G to be an element from the centralizer, so G and F commute with each other, then the fixed point of G will be same as the fixed point of F. So again, G will be hyperbolic. So if I assume this F to be hyperbolic, the centralizer will contain only the hyperbolic elements. If I assume this F to be parabolic, so then the centralizer will contain only the parabolic elements. And if I assume F to be elliptic, then the centralizer will contain all the elliptic elements. Okay, so I'll stop here. So we'll apply this thing to prove some algebraic properties of Fouchian groups.